Hi, this is Dan Bullard, retired electronics engineer, sitting down the front deck of my houseboat again. It ain't summer no more. Thanksgiving's gone by, so it's getting chilly. I want to talk about a number of things. The biggest one I want to talk about first is spread spectrum. And not spread spectrum like your phone or the internet or stuff like that, but there's an interesting technology that came along years ago, and I did some work on it. The FCC requires that you don't put out so much interference from your electronic devices that you cause interference in other devices. Now that's a problem with some devices. You get really high frequency clocks, and those clocks can propagate through the circuit and get out and be radiated out and into other devices. But sometimes it got to be a little bit tough because the electronics run at a pretty high clock frequency, and that clock frequency permeates the circuit board and goes everywhere and could be radiated to other devices. There's a way to get around that, and it's pretty cool. It's called spread spectrum. What you do instead of clocking at one frequency is you kind of jitter the clock frequency around, and you can jitter it different amounts in order to keep it on the move. Now you'd say, well, that's a problem because now the data's moving and all that stuff. Well, yes, but if you do it controllably, then you can keep it down to a minimum and you won't have too many problems. And so there was this company that was trying to test spread spectrum stuff, and they wanted to test it with the Nexus Lightning. And so I talked to salesmen, and they gave me a device, and I looked at what they were doing, and the device would put out frequencies, either the frequency, hey, there's a little boat. It's cold to get out in a boat right now. It would put out one frequency with no jitter. Or you could flip a bit. There were 2 bits to control. You could flip a bit and you get a little bit of jitter. You could flip that bit back to 0 and flip the other bit to a 1 and get a little more jitter. And flip 2 bits and now you got a fair bit of jitter. And it was controllable and it was fixed in a specific area for each setting. So it was really cool, and I did it with an FFT, of course. Me, I do FFTs. That's all I do is FFTs, not all I do. I thought that I didn't have any pictures of this thing, but of course I was poking around and I found my article from Evaluation Engineering on my periodic white noise stuff. They wanted pictures to put on the cover of Evaluation Engineering, and periodic white noise, what does that look like? It looks like white noise. And that wasn't going to be very interesting. And, it's always a problem when you're coming up with artwork for an article that's technical. And so they said, well, what do you got? And it turned out I had these images that I grabbed for this test device that jittered the clock. Okay? And so here it is. It's on the cover of Evaluation Engineering, but it didn't have anything to do with the article, which was periodic white noise. But it looks like noise, doesn't it? It looks like noise. And it uses a pseudo-random number generator. That's what it does. Pseudo-random number generator to generate the shift in frequency. So it's controlled, and it's controlled by 2 bits to control how much jitter you get so that the jitter can be controllable. So that was cool. That was the cover of Evaluation Engineering. So that's 2 covers. I had the Evaluation Engineering and the Test and Measurement World. So that's 2 covers. Somebody called my attention on LinkedIn, one of my supporters called my attention to this video, and I watched it this morning. Understanding current harmonics. Really awful. Really awful. Now, the interesting thing there is they say, oh, harmonics can be a problem, you know. So if you have current harmonics in a 60 hertz system, right, out of the wall, 60 hertz or 50 hertz, it'll cause problems because it can cause overheating of conductors, or it can cause problems with skin effect. And I'm like, skin effect? That's crazy. There's somebody behind me. I can't see them. There they are. So, yeah, I guess the fishermen are getting out. So, the skin effect. Now, this is really interesting. I love skin effect. I was explaining it to my wife. When the frequency in a conductor gets very high, that is, the radio frequency that's going back and forth gets really high, the self-induced voltages, the EMF, in the center of the conductor stops the current from flowing. So there's no current flowing in the center of the conductor. Only current is allowed to flow in the skin. Now that's really interesting. Now that gets up into gigahertz. If you get into gigahertz, that's where that happens. And when I was in college, that was eons ago, but when I was in college, my instructor, Mr. Dillon, who was in the Navy, he told me about how when he was in the Navy, they were putting radar on ships. That was kind of new, right? And so he was helping them put radar on the ships. And so what they did was they put these ceramic insulators on the mast going up to the top of the mast so they could put the radar antenna up there, and they'd have these two lines going up the mast on these ceramic insulators to go up and feed the radar signal to the dish so they could look around. There was a little problem. It worked great until they fired the guns on the ship. When they fired the guns on the ship, what happened? The mast would swing back and forth, right? And it would cause the ceramic insulators to break, and that would put the radar down. And so now the captain, that's one reason I'm in the Navy, not in the Coast Guard or the Air Force or any of those. The Navy, they have to think like this. So the captain is sitting there behind the bridge trying to decide, am I going to fire my guns? Because if I fire my guns, I'll lose my radar. As soon as I fire the guns, the mast will whip back and forth, and it'll snap all the insulators, and my radar will go away because it'll short out the wires going up to the radar dish, and no more radar. So the captain has to think about that, right? Am I going to hold off so I can see what's going on with my radar, or should I fire the guns? And once I fire the guns, my radar is gone. I'll never get it back until after my guys get a chance to rebuild everything. And so the battle's going to have to be over, and we're going to have to be on our way home. So that was a real problem. Now, they were trying to come up with a solution for it. And Mr. Dillon, I don't think that he did this, but he was involved in the decision. If you know anything about RF, you'll know that a quarter wavelength, 1/4 wavelength, is important because at the one end, 1/4 wavelength stub, if you have a short, at the other end, you'll have an open. And so what they decided to do was to take these 1/4 wavelength stubs and weld them to the mast. So they welded these 1/4 wavelength stubs to the mast all the way up to the radar dish, and then they ran the cables up those stubs, the currents flowing up and down those lines. On one end, it's seen as a dead open because it's a short exactly 1/4 wavelength away. And so now, when they fire the gun, the mast will jiggle, but it's not snapping ceramic insulators. That's really cool. So now the captain doesn't have to worry about that. The captain can fight the battle, fire the guns, still see the radar, no problem. So that's how waveguide came about, because they had a conductive surface, the mast, they had the quarter wavelength stubs, and then they just cover it with another conductor, and it's hollow. It's a hollow tube. And that's one way of looking at how skin effect works. In waveguide, current only flows in the skin. You can imagine if it's a square piece of metal, it could have the current flowing up and down the metal, except that the current's not going to flow in the center anyway because of the skin effect. So the current's going to flow only on the skin, and so there's no need to have the entire thick bar of metal. It's just a thin sheet of metal to carry the signal. Waveguide is really cool. I learned a lot in the Navy because, remember, I had a rating that was communications, but I ended up doing radar instead because they had closed the comm school. So I learned about radar, and I learned all about really high frequency stuff in radar school. So skin effect. Now, that's in the gigahertz. That's in the gigahertz. Skin effect does not happen in the kilohertz. It doesn't happen in the megahertz. It only happens in gigahertz. Their video's awful. This is Rhodey and Schwartz. You know, they do high frequency stuff, and they're talking about stuff in the 60 hertz. Now, which harmonic would it be? I don't have my calculator on me. Which harmonic would it be to get into gigahertz from a 60 hertz fundamental? Now, we all know that the harmonics fall off over time, as the frequency gets higher and higher, so you're not going to have much energy there. So skin effect's not really going to be an issue. So these guys are I'm really concerned because what I'm telling you is the truth. I'm telling you the truth about harmonics. But the problem is the entire world believes all this garbage about current harmonics, and there's IEEE standards and IEC standards and all kinds of crazy crap about harmonics, and none of it's true. They're all making it up because they don't know how it works. Harmonics are easy to understand. Easy. Watch my other videos, that's all I gotta say. Okay. I did that video on testing a voltage regulator. And that was really cool. That was for a missile. And I can't tell you which one because I don't want to get in trouble. But the voltage regulator thing is really cool. Now, I work with ATE, automatic test equipment. Okay? Automatic test equipment doesn't use voltmeters. I mean, some do, but not really. The voltmeters are not like this fluke meter. The voltmeters are instruments built into the hardware, and we don't use rack and stack. That's what Tektronix did. Rack and stack is garbage. You don't do that. Nobody in their right mind does that, except for Tektronix and many other places, but nobody really, I mean, I worked in the ATE business, and we didn't do rack and stack. We just refused. We would refuse to do that. For example, I explained to you, when I had to measure frequency using the tester, I could have bought a box and hooked it in, made it kind of a rack and stack kind of thing, but I refused to do that because I knew there had to be a way for me to test frequencies, and that was Larry Getman's idea. Larry Getman came up with the basic idea, and I ended up implementing it, refining it, and making it work. But it was Larry Getman's idea. But rather than do a rack and stack thing, I came up with a way to do it using the tester. And it was brilliant. Again, it wasn't the fastest thing in the world, but it was brilliant. This guy shows this thing on testing a voltage regulator, and it's an interesting video. He shows how to test a voltage regulator, and he shows a counterfeit voltage regulator that doesn't really work. But notice here, I want you to take a look at how he did this. He used a fluke meter remember, I worked for the parent company of Fluke, and if it's accurate, it's a fluke. So I'm sure Fluke meters are fine, but Tektronix's parent company was Danaher, and Danaher owns both Tektronix and Fluke. And you know, I was in marketing, you know. I mean, I learned something about marketing, and you don't name your company Fluke if you're trying to say you're accurate. You know, if it's accurate, it's a fluke. And I got people on interviews. That's how I would interview marketing guys. I would say, oh, if it's accurate, it's a fluke. And oh, yeah, it's really, you know, fluke is really accurate. You don't get it. If it's accurate, it's a fluke. You gotta understand. Okay, we don't test voltage regulators. We don't test anything with resistors and fluke meters, and we don't do any of that stuff. We have specially built instruments. When I was working at Credence, they came up with a special instrument, which was a big tester. It was called an STS 4000, which was basically just like an STS 3000, but it also had all these other instruments. So it was about the same size as an STS 5000. Here's a picture of STS 5000. So an STS 4000 was pretty much the same, but it had all these other instruments, and they had some amazing things. They had a time event digitizer. Now, you should know what a TMU is, a time measuring unit, which measures the time from one event to the next. And that's a really good way of measuring time. But a time event digitizer is the opposite of the sequencer per pin on a Schlumberger tester. On the Schlumberger ITS 9000, IX, GX, KX, they had sequencer per pin. The time event digitizer is the opposite. It looks at a pin and it tells you at this time it went high, at this time it went low, at this time it went high, at this time it went low. So basically it has a clock counting in the background telling you what happened. It went high at this point, it went low at this time. It went high at this point, it went low at this time. So that was a time event digitizer. That was one of the instruments for testing Ford engine control modules. That was a really cool project. And engine control modules for both GM and Ford, that's what they were doing. And it was really cool. Motorola was involved in that. It was really fun stuff. So that was just one of the instruments. They had a lot of cool instruments. Anyway, it's cold out here, so I'm going to go ahead and get inside. So once again, from the river, this is Dan Bullard.